In the rapidly evolving landscape of large language models, one breakthrough stands out: zero reinforcement learning, or zero RL. This technique has transformed how we unlock reasoning capabilities in pre-trained models, by training them directly through reinforcement learning, without any supervised fine-tuning. The result? Models that think step by step, reason through complex problems, and arrive at correct answers, just like a human solving a math problem. But here's the catch. Current zero-RL research is overwhelmingly focused on domains where answers can be easily verified: mathematics, programming, logic puzzles. These are clean, well-defined tasks with ground truth labels. The reward signal is binary, correct or incorrect. That makes training stable, interpretable, and effective. Yet, what about the rest of the world? Real-world tasks, creative writing, nuanced conversations, open-ended problem-solving, don't have clear right answers. How do you reward a model for writing a compelling story, or offering thoughtful advice in a personal conversation? Traditional verification fails. Model-based reward models try to fill the gap, but they come with a dangerous flaw: reward hacking. You see, generative reward models often learn to maximize length rather than depth. They reward verbosity, not insight. So instead of thinking deeply, the model just keeps writing long, repetitive, hollow responses that sound impressive but lack substance. This is not reasoning. It's performance art. So how do we fix this? Our team at Tencent has developed a new paradigm: General Zero RL, a unified framework that bridges the gap between verifiable and non-verifiable domains. We're not just expanding Zero RL to new tasks, we're making it smarter, more stable, and more generalizable. Here's how it works. We combine two types of data in a single multitask reinforcement learning pipeline: reasoning tasks with verifiable rewards, and general tasks with generative reward models. The key insight: the reasoning behaviors learned in math and logic can be transferred to open-ended domains, if we train them together. On the reasoning side, we use a verifier model, a second LLM that checks whether the final answer matches the ground truth. This gives us a clean, binary reward, one for correct minus one for wrong. On the general side, we train a generative reward model based on QN2, 5-72b, to evaluate response quality on a scale from -5 to 5. But here's where it gets clever. To prevent the model from gaming the system by inflating response length, we introduce a smooth length penalty, a novel regularization strategy that penalizes the difference between the length of the reasoning process and the answer. Let's unpack that. Imagine a model generating a 1,000 token answer, but only 100 tokens of real thinking. That's reward hacking. Our penalty doesn't just punish long answers, it punishes asymmetry. If the thinking content is too short relative to the answer, the model gets penalized. The longer the answer grows, the more the model must extend its reasoning in tandem. This forces a balanced, meaningful development of thought. We also apply a secondary length penalty on the answer itself, capping it at a maximum length, and applying a soft penalty as it approaches that limit. This prevents runaway verbosity, while still allowing room for depth. All of this is trained using group relative policy optimization, GRPO, a state-of-the-art RL algorithm that avoids the instability of KL divergence terms and uses token-level policy gradients for better convergence. We train on QN3-8B base and QN3-14B base, using a carefully curated mix of data: 178,535 math and STEM prompts from our internal collection, 125,798 filtered from Web Instruct, and 36,125 diverse, realistic conversations from ShareGPT. Now the real test: does this work? We evaluated our models across three categories: math reasoning, general reasoning, and general tasks. On math benchmarks like Math 500, AIME, and Olympiad Bench, our General Zero QN3-14B model achieved 92.4% accuracy, surpassing even Deep CCAR 10 QN32B, a model trained on far more data and with a larger base. On general reasoning tasks like MMLU-Pro, GPQA Diamond, and Super GPQA, it outperformed all competitors, including models trained exclusively on reasoning data. But the most striking results came on general tasks: Arena Hard, WritingBench, WildBench V2, and Alpaca Eval 2.0. While models trained only on verifiable tasks, like General Reasoner or Uni-Reason, collapsed into poor performance on these benchmarks, our General Zero models didn't just hold their own. They beat the QN3 Instruct baseline, which was distilled from much larger teacher models. And all this was achieved with just zero supervised fine-tuning and a small set of open-source general prompts. Why? Because the multitask training forced the model to learn reasoning as a general capability, not a domain-specific trick. To see the difference in action, compare two responses to the same prompt, explaining the human perspective hierarchy in an organization. One was generated by a model trained only on general data, no reasoning. The output: a smooth, polished, but shallow summary. It mentions CEOs and individual contributors, but there's no structure, no logic, no real thinking. Just a well-written paragraph. The other was generated by our multitask-trained model. It starts with a clear plan: define the concept, map the hierarchy, explain differences, discuss challenges. It breaks the problem into steps, uses markdown formatting, and delivers a comprehensive, multi-dimensional answer. This is not just a response, it's a reasoning process. And it wasn't just on writing. In a creative task, writing an email to request a headcount backfill, the model didn't just draft a message. It thought through the strategy. Why now? Why Zicheng? What's the team impact? It structured the email with a clear subject line, rationale, and tone, all before generating the final draft. This is the power of multitask 0RL with length penalty. It doesn't just make models smarter, it makes them think. We also conducted ablation studies to prove it wasn't magic. When we trained only on reasoning data, performance on general tasks dropped by 13.3%. When we trained only on general data, the model spiraled into reward hacking. Length exploded, reasoning didn't grow. But with our full framework, both thinking and answering evolved in harmony. And we didn't stop there. We visualized the training dynamics. On reasoning data, both think and answer lengths grew steadily, natural, proportional, meaningful. On general data, with the length penalty, the thinking process expanded alongside the answer. Without it, the answer ballooned while thinking stayed flat. The penalty wasn't just a fix, it was a catalyst. Now this isn't perfect. We didn't include code-related tasks, because they require execution environments like sandboxes. But the principles apply. Reward hacking is a universal problem. And our solution, multitask learning, smooth length regularization, and balanced growth, can be adapted. In conclusion, General 0RL is not just an incremental improvement, it's a paradigm shift. It shows that reasoning isn't confined to math and logic. With the right training strategy, we can elicit deep, structured thinking across all domains: writing, conversation, strategy, creativity. We've proven that 0RL can go beyond verifiable tasks. We've shown that reasoning can be generalized, stabilized, and scaled, without supervision, without massive datasets, without sacrificing coherence. This is the future of intelligent language models, not just answering questions, but thinking through them one deliberate step at a time. And that's not just a technical advance. It's a step toward truly general AI.